Hello everybody, welcome to our first video solution to Quiz 10. This is from Spring 2023, Math 302 at Cal State Fullerton. And in this problem it says Dr. Glesser, wait, that's me! Hey, I'm Dr. Glesser! Oh, cool. Dr. Glesser decided to try to build his own ring without unique factorization. Okay, so this is something based on what we've been doing in class. We look at what in class I called the Dedekind integers, which was z adjoin theta. Okay, so that's what we've been dealing with in class, the Dedekind integers. Z adjoin theta, where you recall theta squared is -5. And we saw that in this ring, z theta, there you lose unique factorization because you had, for example, 6 that could be written, well, of course, 2 times 3, but also as 1 plus theta times 1 minus theta. Okay, so recall everything in z theta, well, it looks like what you see over here on the left, a plus b, well, instead of a delta, it'd be a plus b theta. Okay, so you don't have unique factorization because, in fact, in this ring, all 4 of these are indecomposable. You cannot factor them without using units. All right, so here we are coming up with a new ring, z delta, and here delta squared is equal to -7. So I mentioned that there's a norm map, just like before, only now instead of the norm giving you a squared plus 5b squared, which is what happened for the Dedekind integers, it gives you a squared plus 7b squared, and I just tell you it satisfies the usual properties of the norm map. The most important, of course, is the multiplicativity property. Okay, now 8 can be written as 2 times 2 times 2. All right, let's see here. So 8 is equal to 2 times 2 times 2. And that is said to be a factorization into indecomposable elements, which we may assume without proof. So all of these, of course, they're all 2's, so it's really only one statement, are indecomposable. Okay, so part A, find another factorization of 8 into indecomposables. And well, let's just read ahead to part B for a moment. Did you prove that the factors in your factorization above were indecomposable? If so, great. If not, we have to prove it. So the whole point is it's not good enough just to say, oh, yeah, see, these are indecomposable. No, you need to actually explain that they are indecomposable, like why they're indecomposable. And of course, we'll use the norm map. But before we can do that, we have to actually find a factorization. And the hope is that you actually have this original factorization from class in mind, because a similar thing will hold here. If I do 1 plus delta times 1 minus delta, well, this is a difference of squares. I know it's going to give me 1 minus delta squared, right? 1 squared minus delta squared. Okay, but delta squared is -7, so this becomes 1 plus 7, which is equal to 8. Hey, look at that. It works. Now, it's fine. We found a decomposition, but we need to actually show these are indecomposable. All right, so that's the goal, right? Are these indecomposable? How do we do that? Well, we're going to do it, we'll pick one of them. So we're going to show that 1 plus delta is indecomposable. Now, what did that mean? Well, to be indecomposable, that meant that if you ever try to factor 1 plus delta, one of the factors has to be a unit. So let's assume we do have a factorization. So assume, let's call them W and Z are in Z delta such that 1 plus delta is equal to WZ. Okay, and so then the approach here is to apply the norm map. Now, the norm of 1 plus delta is going to be 8. Either we see that because, hey, look, this is actually 1 plus delta times its conjugate, and we know that gives the norm, and that's equal to 8. Or you just compute it using this formula we had up here. The norm will be, in this case, 1 squared plus 7 times 1 squared. Okay. Either way, we get that. But now this is the same as the norm of WZ, and we can use the multiplicativity property. And we get now that the norm of W times the norm of Z is equal to 8. Okay, so what are the possibilities, right? We know that the norm map, this is a map, in this case, from Z delta to Z greater than or equal to 0. So we know that these are non-negative integers that multiply to give me 8, so I could have 1 and 8 or 8 and 1. And if it was either of these cases, I would have something with norm 1, and that's one of our usual properties. We know that if the norm of something is 1, then that something is a unit. Okay, so in either of these cases, we would have a unit. And if we're trying to prove that 1 plus delta is indecomposable, that's great, right? If all we have are units. Okay, but of course there is kind of this other way that you can multiply to get 8, which is you could do 2 times 4. And of course we could also have 4 times 2. These are essentially going to be the same situation. Okay, so here's the question. Is it possible that we're in one of these two situations, either 2 times 4 or 4 times 2? Well, for that to be possible, it would have to be the case that 2 could be the norm of something. So can it be the case that 2 could be written as a squared plus 7 times b squared? Well, let's see here. So first, this 7b squared, that gets big really quickly, right? If b has absolute value at least 1, then b squared will be at least 1, and so 7b squared will be at least 7. So 7b squared will be at least 7, and which of course that would imply that a squared plus 7b squared would also be at least 7, which is greater than 2. So that means that b cannot have absolute value at least 1. Well, b is supposed to be an integer, right? That doesn't leave a whole lot of options, right? So this would imply that b is equal to 0. But if b is equal to 0, then 2 is just equal to a squared, which cannot happen for the integers. 2 is not a perfect square. This is a contradiction. So it is not possible for 2 to be the norm of any integer or any z delta element, which means neither of these is possible, right? Both would assume you have something with norm 2. So these are both impossible. So we conclude we must be in one of these other two cases, in which case we have a unit, right? So this would imply W is a unit. This would imply Z is a unit. And therefore we've determined if you can factor 1 plus delta, then one of the factors must be a unit. Okay, so this implies 1 plus delta is indecomposable. Now, what's going to happen if we replace 1 plus delta by 1 minus delta? Well, this only relied on the norm, and the norm of 1 plus delta and 1 minus delta are exactly the same. So similarly, 1 minus delta is indecomposable. All right, we're not going to show both. Okay, so there we go. That's how we can prove that something is indecomposable. Even in a new ring that we haven't seen before, you'll see it's really the same type of argument that we used for the Dedekind integers or even for the Gaussian integers. All right, we will see you next time.